Okay, time to get going. So we're recording. Here's where we left off last time. So we were talking about how to use derivatives and antiderivatives, right, to relate position, velocity, and acceleration. And so we already talked about how, well, look, the acceleration is just the derivative of velocity, right? And position is the antiderivative of velocity. Right, so this is just a matter of doing this one coordinate at a time. Right, pretty straightforward. And where we left off, if I remember correctly, I think, is we didn't talk about how to evaluate the what some people call the integration constant, which fussy me, I would prefer to call the anti-differentiation constant. By the way, where that comes from is I think it's there's an inappropriate conflation of integrals and antiderivatives. They're importantly different. They kind of get used sort of interchangeably, at least the term integral does. I think this is a problem, right? So if you're not entirely sure about the difference between integrals and antiderivatives, I encourage you to look at my miscellaneous topics talk on that topic. I have a bunch of such talks. They're on the YouTube channel in the miscellaneous topics playlist, and one of them is called "What is an Integral?" Right. So if you're not crisply clear on the distinction between an integral and an antiderivative, you probably want to watch that. Okay, and it addresses other aspects of integrals as well. Okay, but back to the point here. Here's the myth that is a real problem. A lot of people think your integration constant is the same as your initial value, and that is just not true. It's just straight up not true. Here's an easy example. Look at our integration constant, ends up being 2, 5. Look at the initial condition that was given. They're clearly not different. Indecision. They're clearly different. They're clearly not the same. Right? So, why do some students think that they're supposed to be the same? And there is actually a pretty good answer to that question. In most, let me not overstate it. In some high school math classes, they only use polynomials. Right? And so the thing is, if these are both polynomials, then their antiderivatives will also be polynomials, but they'll all be polynomials with a factor of t in them. And if they all have a factor of t in them, then when you plug in t equals 0, what you actually get here is the 0 vector. And then when you look at this equation and you interpret, okay, well, we're looking at t equals 0, and so that position allows me to infer what this integration constant is. Well, the difference between R and C is 0 in those cases, because arbitrarily and for no particularly good reason, they're only using polynomials, right? So it's a coincidence, right? It's a really unfortunate, misleading coincidence that is a result of, I'm going to say, bad choices on the part of some instructors. So make sure to realize they're not the same. If you want to know what your integration constant is, you look at this equation, you plug in t equals 0, right? And t equals 0, plugging in makes this go to there. And then this evaluates however it evaluates. And then solve for C. Right? So that equation turns, in this case, into that equation. And then you want to know what C is? Fine. Solve for it. Nothing to it. Okay. So, anyway, not always the same as the initial condition. So, be warned. Alrighty, so now there are a couple other things to say in section 3.1. There's also a bunch of other stuff in 3.1 that is beautiful mathematics that we don't have time for. It's not part of the prerequisite trail of what we're ultimately trying to build to. And it's historical and wonderful and interesting, and you're not responsible for it. We just don't have time to justify it. So I'm referring here to the Kepler stuff. That's pretty pretty clearly labeled, I think, in the book. You're not responsible for most of that. Exception, as is noted on the content syllabus, you are responsible for for Proposition 1.4. It's somewhere in amongst all that Kepler stuff. And it's a couple of statements about what we're going to loosely call product rules for derivatives of vector valued functions. And so, of course, there's a dot product rule and there is a cross product rule. And don't they look exactly like they kind of ought to? It's not surprising that these are true, but it's important that you know that these are true. And by the way, they're also easy to prove. Just multiply it out and use single variable calculus results. And it falls out pretty quickly. Okay. All right. So we're going to move along now. Back to Chapter 2. Remember, we did a quick jaunt into Chapter 3 because there's a certain point of view about derivatives, understanding derivatives as velocities that I think is super valuable. It's my favorite way to think about the chain rule, is to come at it from the point of view of derivatives as a relationship between velocities. So, so here's the point of view I'm going to start with. By the way, we're going to start with single variable calculus. And I know that y'all already know single variable calculus. My purpose here, to spending an entire page of notes on the single variable chain rule, is not to tell you something you don't know. I already know that you know the single variable chain rule. My purpose here is to set up an analogy, right? So there is a particular point of view on the single variable chain rule that I think generalizes to the multivariable chain rule very nicely, very smoothly, very naturally. Right? I think it's an easy foot in the door, right? But the catch is, you do have to, if you want to take this nice little foot in the door, you do have to take just the right point of view on the single variable chain rule. There are several points of view on the single variable chain rule. I'm all for them, but for the moment, we need to take this point of view. All right, so here it is. The single variable point of view on derivatives that I want to push is that it's a relationship between an input velocity and an output velocity. Now again, old news. You all know this from single variable calculus. It's a point of view anyway on something you all know from single variable calculus. And if the input point is moving with some velocity and the output point is, as a result, moving with some velocity, the derivative is the thing that turns the one into the other. Specifically, the derivative is the factor that you multiply by input velocity to get output velocity. Right? Now, there's many different points of view on the derivative. I'm all for them. For the moment, we want to take that point of view on the derivative. Everybody good? All right, so derivatives are factors. They're multiplicative factors. And with that point of view, let's look at a composition of functions. By the way, there's some algebra on the page that I would almost go so far as to say I kind of regret putting it on there. It makes it look like there's a bunch of algebra that is required to understand this point, and fundamentally it kind of isn't. So I'm going to suggest you kind of ignore all the algebra on the page unless you really want to dig into if you don't trust me or if you don't think that this is a satisfying case that I'm about to make, then yeah, sure, look at the algebra. But let's try in advance to just not look at the algebra. Notice what I have is a single variable function that I'm composing with another single variable function, in the sense that what comes out of the first one is then what's going to go in to the second one. Right? What comes out of F is what goes into G. And let's think about the related velocities of X, Y, and Z. So X might have some velocity, and that will, of course, cause Y to have some velocity, and that will, of course, cause Z to have some velocity. Now, I remind you, with this established, that we've got these three different variables, each of which is changing, each of which has a velocity. Let's remember that the derivatives of F and G we're going to think of like so. We're going to think of them as being factors. It's what you multiply input velocities by to get output velocities. Yeah?
Just to understand, is f the same thing as dy dx? Is it like
yes?
Is the transformation?
No. F is how y is a function of x. Dy dx is the derivative of f.
Okay.
Yeah. F takes x input and gives y output.
So the derivative is just the derivative of that function.
The derivative, yes. Dy dx is the derivative of that function f. That's right. Yeah. Cool. Everybody good? Okay. All right. So with this point of view, the derivative is a factor that you multiply by input velocities to get output velocities. From that point of view, well, f prime, let's see, I'm making color choice decisions here. F prime is this factor. Let's see here. G prime is this factor. And now let's just think for a quick second here. Altogether, what is the overall total factor, right? So I did the green factor, and then I multiplied by the blue factor. Altogether, what is the combined factor? Now, silly little exercise. Let's suppose you got some numbers, and let's suppose you start by, you multiply by 4, and then after that, you multiply by 5. Altogether, you've multiplied by 4 times 5. That's really all the chain rule is saying. All the chain rule is saying is that overall purple factor, altogether, when you multiply by a green factor and then you multiply by the blue factor, altogether, the overall factor is the product of those individual factors. And that's really all the chain rule is saying here, right? So the derivative of the composition is the product of the derivative of the first function and the derivative of the second function. Now, again, you can look at the algebra if you like. I think it's more of a distraction than anything else. Factors multiply, I think, is a nice take on what the chain rule is doing. Okay, so again, many different ways to think about the chain rule. You may have a different favorite point of view. Cool, all good. But this is the point of view that's going to generalize really nicely in the multivariable setting, and let's do that now. And I got ahead of myself. I'm sorry. Just a real quick little pithy little summary here. When you're talking about derivatives, when you compose functions, the result is a product of the individual derivative. So I think this rolls off the tongue very nicely. Differentiation turns a composition into a product. I think that's pithy and satisfying. Something to think about. Okay, so now let's try to do this in the multivariable setting. And here's our starting point. And I'll remind you, as previously discussed, we're going to think of the derivative as a relationship between input velocity and output velocity. And here it is. If you have an input velocity and you want to know the output velocity, the derivative is the factor that you multiply by the one to get the other. And the asterisk on this is, it's a matrix factor, right? But it's still a factor. And why is it a matrix? Well, because, we're turning input vectors and output vectors, and that's what matrices do, right? And specifically, this DF we saw is the matrix that does that for us, for a differentiable function. So just like in the single variable case, we're going to start from this point of view that a derivative is a factor relating input velocities and output velocities. And then, just like in the single variable case, we're going to look at a composition. So notice we'll start with, let's see here, we have a multivariable function here, 2 variables in, 2 variables out. And now we have another multivariable function here. The 2 outputs from F being the 2 inputs to G, which then also has 2 outputs. Right? And we could talk about the composition. The composition is a function that takes these 2 inputs and gives us these 2 outputs. So again, we're just composing. And again, if you think of the derivative of f as the thing, it's the factor that you multiply by x prime to get y prime. And if you think of the derivative of g as the factor that you multiply by y prime to get z prime, all right, we'll play the same game. I've got some vector. I multiply by one matrix, and then subsequently I multiply by another matrix. Altogether, I've multiplied by the product of those matrices. That is, the factor that turns x prime into z prime is just the product of those individual factors. And again, it's just, it's a lot easier to think of it in terms of factors. When you multiply by factors in succession, altogether you've multiplied by the product of those factors. It rolls off the tongue really nicely. And that's what this multivariable chain rule says. The derivative of the composition, the factor for the composition, is the product of the individual factors, df and dg. And do be careful, by the way, to get the order, the correct order. Oh, I colored that wrong. Sorry. Dark blue. Here we go. Do be sure to get the order correct. You'll notice something unfortunate and confusing about the way this lays out on the page. Hey, how come the green one's on the left in the diagram, but it's on the right in the algebra? Well, that's how we decided, rightly or wrongly. A lot of people would say wrongly, but this is how we decided to represent how matrices multiply by vectors. We multiply matrices by vectors by putting the matrix on the left. And diagrams, arbitrarily, for whatever reason, diagrams go toward the right. So this fact that the colors seem to be kind of backwards from each other is it's an unavoidable consequence of long-established notational conventions that in retrospect are kind of unfortunate. So heads up, there is no workaround on this. You've got to just always, don't think in terms of left and right. Think about which one acts first, which one acts second, and what does that mean in whether you're looking at the diagram or whether you're looking at the algebra. Make sure to interpret that appropriately. Right. Okay. How we doing? Everybody all right? Notice, again, same basic idea. We've multiplied by a factor and then another factor, and altogether we've multiplied by the product of those two factors, just like in single variable. Okay. So I hope this is a believable result. Again, now you can look at the algebra if you like. I don't think it's particularly helpful, really, but suit yourself. Again, notice differentiation turns a composition into a product, this time a product of matrices, because of course the derivatives are matrices. What do you think? Everybody good? Real quick, it would appear that the argument that I just made is peculiar to two dimensions. After all, look at the picture that I drew, right? Everything in here is two-dimensional. That's two-dimensional. That's two-dimensional, etc. Oh my gosh, what if we had three-dimensional domain or something else somewhere along the line? And here's the point. I like to do this just for the humor of it. But the reason that you interpreted what I drew here as being two-dimensional is because I drew two axes. Now it's three-dimensional. Right, same argument. It's still the df is the matrix that turns x prime into y prime. Now df is now a different shaped matrix. Yeah, sure, right, yeah. But it's still, df is still that matrix. And it remains that the product of factors is the overall factor, and the argument doesn't change at all. And likewise, anywhere else along the line, like if I were to make this, three-dimensional, again, we have matrices that are factors, and factors multiply. It's the same argument. So this works for any dimension, not just two dimensions as I have it drawn. Okay, so with that in mind, let's do an example. Here we go. I've got a couple of functions given, f and g. Now, very importantly, we're about to compose. We're about to compose in the sense that what comes out of f, right, is going to be what goes in to g. Right? You see that this is the, what comes out of f is what goes into g. And again, notice that the way it looks in the algebra is not the same as the way it looks on the page. And again, heads up. Right? You've got to be careful about that. Okay, so that said, I've been asked now to find the derivative of the composition. That'll be the first thing we'll talk about. Next, we were asked to find this particular partial derivative. We'll come to that next. So for the moment, let's just focus on the derivative of the composition and recalling from above, derivative matrices multiply. All right, so just going to straight up copy that down. Derivative matrices multiply like so. And notice some of this information was straight up given, right? We have a bunch of given freebie information here. I had to give some givens because I didn't write explicit formulas for f and g. Very often, by the way, this is how stuff works. So, okay, well, df at 1, 2. Boom. Given. Write it down. Let's see here. Now, next, there's a little bit of a tweak that we're going to have to deal with here. I'm going to need to know the derivative of g at f of 1, 2. I was given the derivative of g at 3, 1, 0. So those do not immediately appear to be the same matrices. But then you notice, very conveniently, f of 1, 2 is 3, 1, 0. So, in fact, that purple matrix that we were given is exactly the dark blue matrix that we actually need. So, again, sometimes you got to, interpret accordingly. So, this matrix, what I need, again, write it down. Right, so all together, if you want to understand the product, right, here's our derivative of our composition. It's the product of those two matrices, and I just multiply them, and y'all know how to multiply matrices, so boom. How we doing? All right, now heads up, warning. Reminder, let me start with a reminder. This is a class about reasoning and comprehension of ideas. Right? This is not a memorize and regurgitate. This is not a rehearse and execute kind of a class, right? So part of my job then is to make the distinction of who actually understands the ideas and who's kind of doesn't know what's going on and has rehearsed some little algorithms and is hoping that will just work. So I have to try to distinguish between those. And one way that I do that is I set up questions in such a way that someone who understands will get it right, and someone who doesn't will make a mistake exposing what they don't understand. That's how exams work, right? So what I did here, and I do this on exams all the time, notice, again, the matrix that I wrote down on the left ended up being on the right. And the one that I wrote down on the right ended up being on the left. Now, again, if you are heads up, if you're paying attention as you should to, wait a minute, which one's first, which one's second, what does that mean diagrammatically, what does that mean algebraically, how does matrix multiplication work? If you're thinking actively, as everyone should, about that, there's no confusion, right? You write down the chain rule in the correct order, and green is green and blue is blue, and there's nothing to it, right? But if you're oversimplifying, if you're not paying attention, then you'll naively write them down in the wrong order. Does everybody see the landmine there? This is an easy one to mess up, right? And the way we deal with situations that are easy to mess up is we become aware of the confusion and we think to avoid it. Right? So heads up, that is going to be part of your responsibility on questions like this, is to think it through and to get those matrices in the correct order. Now, for whatever it's worth, you'll notice if I were to get these matrices in the wrong order, you'd have a square peg, round hole situation, right? You can't multiply the matrices, and that would be your tip-off. In this case, it will not always be like that. Right? There are some cases where when you get the matrices in the wrong order, they'll multiply just fine, and you will not have such a tip-off. So, heads up. How we doing? Everybody good? Okay. All right, now next question. We were asked to compute this partial derivative right here. And we got to think to ourselves then, okay, wait a minute, I've computed the derivative matrix. The derivative matrix is this. That's the derivative of the composition. I am interested in the derivative of one of the output variables of the composition with respect to one of the input variables to the composition, right? So again, the composition takes F's inputs and gives G's outputs. So I'm looking for a partial derivative of the composition. I have the derivative matrix for the composition. And don't forget, the derivative matrix is made up out of the partial derivatives, one of which then is what we're looking for. So the way we're going to get this straight, let's see, I need just a little bit more screen. There we go. Let's see here. We are taking a partial with respect to the first input variable. Remember, columns correspond to input variables. So because we're looking for the partial with respect to the first input variable, what we're interested in is in the first column. Is that cool? Okay, note next, we're looking for the partial of the third output variable of the composition. Output variables correspond to rows. If you're looking for a partial of the third output, that partial will be in the third row. So the partial that we're looking for is in the first column, third row, and is therefore 3. Everybody good? Yeah.
Why is that output variables correspond to rows?
Oh, that just goes way back to, if you look at the formula for linear approximations, this is way back here. Oh, went too far. The formula for a multivariable linear approximation, this being our motivation for how to write down the derivative matrix, this is what it has to be. Columns have to correspond to input variables to make it work. Yeah. Right. Okay. All right. Let's see here. There we go. Okay. All righty. So moving along. A couple of special cases. You'll notice I have these labeled as, y'all can read. I think most of this is pretty straight read. I just want to point out some of the matrix shape stuff that kind of makes all this work, and then I'm going to let y'all read the examples. Again, I think it's pretty straight read. In this special case here, we're considering the special case where there is only a single input variable in the first function of the composition. And here's what one of the consequences is. One of the consequences is that this first function then gives position in Rn as a function of time. That's a parametric curve. Yeah, okay, well. Oh, hey, here's another consequence. Again, let's look at the composition now. That composition is a function that gives position in Rm as a function of time. It too is a parametric curve, right? And what we have here then is arguably that f is a function into which we're moving around in a parametric curve in Rn, and there's an image of that of course, is another parametric curve in Rm. And notice what happens to the chain rule. Now, of course, these green and blue functions have a single input variable. That means their derivative matrices have a single column. And if you think about it, that means that this is an input velocity, and this is an output velocity. And as we already knew it should, this just kind of restates this fact that derivatives are relationships between input velocities and output velocities. Now, I emphasize this is not a new result. I'm not claiming to have proved anything here. In fact, if I claimed such, I would be making circular reasoning, because we assumed, right, this interpretation of derivative matrices while proving the chain rule. You can't then use the chain rule to prove that point of view about matrices, right? So this is not, I'm not proving anything. I'm just making the observation that there is a point of view on the chain rule that effectively is a restatement of what we already knew about what derivatives do. They turn input velocities into output velocities, and case in point. So this, you'll find in some cases that statements of this sort are referred to as statements about derivatives, and in other cases, same story, people will talk about them as being because of the chain rule. So that's, take your pick. Okay, so again, old news. This example is just an example of, again, old news. We are given a scenario where we have an input velocity given to us, and the question is to compute the resulting output velocity, and we do so by multiplying by the derivative of that function. So details for y'all, I think, very readable. Okay, next special case. We're still going to continue with having one input variable. That means that we have one column in each of those. But now we are also going to assume, color choices. I kind of like to use the blue and the green. Oh, gosh. Okay, fine. Let's assume now also a single eventual output variable. Well, how does that change things? Well, okay, look, all that does is it means that this function has a single output, which means that its derivative has a single row, right? And it also means that the composition has a single output, and therefore its derivative also has a single row. Right? So the punchlines, right? The point to this is, and that means that this eventual overall derivative we're looking at, well, in fact, you can see it right here in the picture. Let me get rid of the mess. That composition derivative we're looking at, that's a single variable function. Single variable in, single variable out. That is a Calc 1 style, good old-fashioned regular function, right? And it also has the effect that the derivative here, being a single row matrix, can be interpreted as a dot product with the gradient. And again, we talked about that last time or the time before, fairly recently, that when you have a single output variable, a derivative matrix has a single row. And multiplying by a matrix is not that different from dotting with a vector. It's basically the same arithmetic. So again, is this really news? No, not really. We already knew this, right? But again, it looks different because of how we write the derivative. And so it, again, is sort of another, it is sometimes considered a fundamental property of gradients, and it is sometimes considered a special case of the chain rule or an example of the chain rule. And again, heads up. Okay, so again, example, very readable. We relate input velocities to output velocities by dot product with the gradient, appropriate to that circumstance. Okay. All right, different point of view on the chain rule. First, let's remind ourselves, here's the chain rule. Let me go ahead and sort of label. This is my DF, and this is my, this is my DG. And this then is the derivative of the composition G compose F. Right, so this is just expanding it out by coordinates. And again, the coordinates are given there, right? So F takes X's to Y's. So notice that its derivative matrix is the partials of the Y's with respect to the X's. I'm just expanding what these derivative matrices are, one sort of element at a time, and then likewise for the G and likewise for the composition. This is what that turns into. Make sure you're clear on those details. Fill in those blanks. And now all I'm going to do is say, well, let's just kind of multiply this out. Forget about the whole matrix. Maybe I don't need the whole matrix. Maybe I have very specific goals in mind for whyever it is I might be thinking about these functions in the first place. Maybe all I need to know is this one single partial derivative. I don't need the whole derivative matrix. Don't make me compute stuff if I don't need it. Valid. Right? All right. Well, how do you multiply? One element at a time. You dot the corresponding row of the left matrix with the corresponding column of the right matrix. Again, old news, right? Linear algebra. You all remember how to multiply matrices? And when you multiply that out, this, you can straight up see the dot product happening here. You can see those factors on the left from that green row. And you can see these factors on the right from that blue column. And all together you get a new form of the chain rule, what's you might call a coordinate form of the chain rule. And it's very commonly written this way. I think it's a lot less natural that way. I'm not really pushing this point of view, certainly not right now. Let's compare and contrast, by the way. Which do you think is easier to understand and easier to write down? Some long formula with dots in it and a bunch of different terms about relationships between variables that connect in different ways, or factors multiply. And I think that makes a lot more sense myself. Right? And that's why I like to start with that. But that said, this is very convenient. And sometimes you truly only need one partial derivative. And this gets you right to it. This spares you having to otherwise compute a bunch of elements of a derivative matrix that you don't end up even needing. Right? And then likewise, these. I don't have to compute any of that. I also don't have to compute anything as sort of outside of the one element of the product matrix that I'm just not interested in, right? So this spares us all of the red and gets down to the tight, streamlined computation of exactly what we need. How are we doing? Is everybody with me? Okay. All right. Okay, now I got to give you a warning. Very tempting. Lots of students, oh my gosh, I see this so often on exams, and it's super wrong. Super duper wrong, right? It's not just that you'll get a wrong answer, it's that the reasoning is nonsense. It's so easy to step on this landmine. Please don't let this be you. Here's the landmine. A lot of students, this happens all the time, a lot of students will look at this, in their process of writing down the whole thing, they'll stop at mid-process and say, hey, you know what? I feel like that and that cancel. And then that is the numerator I'm supposed to have, and that's the denominator I'm supposed to have. And so, I think we're done here. And then they don't write down the rest of the equation. Now you see the allure there, I'm sure. That's tempting. It's very tempting. I'm sure that's why so many students do it and then get wrong answers. So first important observation, make sure to realize this is wrong. First way I know it's wrong, it's inconsistent with what we've already established to be true. That's, minor point, right? It clearly gets the wrong answer. But I also want to emphasize what's wrong with the reasoning. It's wrong to think that this and this are the same. They are not the same. I blame the notation. The notation for partial derivatives is pretty unfortunate, right? And this thing that looks like a numerator and a denominator of different fractions is not a thing by itself. Stand alone, if you just write down partial y1 and that's all you write down, I don't know what that means. For example, let's look at it in this scenario here, right? If I look at partial of zi with respect to y1, what's going on there? We're taking a partial derivative of our sort of second function. We're holding all the other y variables constant because that's how partial derivatives work, right? So in this scenario, the other y variables are constants in that story there, right? Partial y1, the denominator of that fraction, is a player in a story in which those other y variables are constants. Okay, fine. Now let's think about this other side over here. Let's think about what's going on in this story. In this story, we're holding various x variables constant, but we're changing xj. And when you're changing xj, let's see, let me go back up to the... If you make changes to one of those variables, you make changes to the inputs to f, guess what? All of your outputs are going to change too. So in this story, right, these y variables, well, let me do it like this. These y variables that were constant over here are now, very importantly, not constant. So what we have here is, in both cases, partial y1 is supposed to represent how much y1 is changing, but in totally different scenarios, completely different stories. It's like if you're reading two books, and there's a character named Steve in each book. Yeah, they're not the same guy. Right? So, same deal here. These two partial y1s, same name, different critters. Right? So, you can't cancel them because they're not the same thing. And yeah, the notation makes it look like they are, and but they aren't. And yes, I too am frustrated by the awkwardness of this nature of the notation. And I don't have any particularly better ideas that aren't super bulky and unwieldy to the extent that we would not like it. And B, even if I did, I don't get to decide what notation planet Earth uses. Right? So this is unfortunately the notation, unfortunately or otherwise, this is the notation. This is the resulting unavoidable landmine. Don't step on that landmine. You cannot cancel. They are not the same thing. It's nonsense reasoning. And... minor note, it'll get you the wrong answer. Okay, so keep all that in mind. All right, so now how do we think about this? How do we think about the chain rule? This coordinate form of the chain rule. There's a really nice way to think about it. Very helpful. And by the way, again, I make the case. This is a lovely tool. You will use this a lot. And if you're going to use it a lot, it's nice to have an intuitive sort of point of view on where does it come from that doesn't require bringing out the big guns of the derivative matrices that are so bulky. So here's the point of view. We're looking at how zi changes, right? And keep in mind we have it set up that the z's are functions of the y's. This is what we call g on the previous page. Right? And we're interested in how that changes with respect to xj, which remember is the input to the first function that on the previous page we called f. Okay, so this is our diagram, you might say. And now it's a partial derivative. Partial derivative means I'm holding all of these variables here constant. Right, so both of those variables, all of those variables are constant, just xj changes. And now let's just kind of think about what happens here. Right? I mean, this is kind of play along. When I change xj, there's a bunch of things that are going to happen. All the y variables are going to change as a result, as we previously noted. But in particular, when you change xj, that is going to cause y1 to change. And we have a tool for writing down this relationship. Per change in xj, how much does y1 change? That's that factor right there. Okay. All right. Now here's the thing. Independent of what happens with all of the other y's, we'll come to those in a second, but looking only at the y1, the mere fact that y1 is changing, ignoring all the others, the mere fact that y1 is changing will contribute a change in zi. And we have a tool for writing that down too, right? So the factor that describes how y1 changes alone will contribute to zi changes is that right there. So here's the way I'd like to think about this then. I like to propose that a way to think about this is that this term is the result of keeping track of how xj changes propagate along this path to contribute to changes in zi. Right, so every term arguably comes from a path. And you can play this game all the way down the line, looking at all the different variables. Let's get rid of sort of all that stuff. Let's go down to the very last one, looking at that path. Well, we have a way to write down how xj changes contribute to ym changing, and we have a way to write down how those ym changes alone will contribute to zi changing, and bam, there you go. That path creates that term. Right? So a nice way I think a really nice way to think about this entire form of the chain rule is that each term corresponds to a path. And et cetera, et cetera. Let's see here, et cetera, et cetera. Lastly, this term arguably comes from this path. So terms correspond to paths, and then you will also notice that each path is identified by one of these, what I call intermediate variables, and I think that's a somewhat standard term. So paths, let's see, let's say that terms correspond to paths, paths correspond to intermediate variables, and so the sort of the nice streamlining of all of this is that each term corresponds to an intermediate variable. You can think of this term that has the partial y1s in it that you're going to want to you're going to feel the urge to cancel, but that of course you can't, right? That comes from the y1 intermediate variable. And then likewise, this term here that has the yms in it that again you're going to want to cancel, but you can't cancel because you can't do that. That corresponds to the ym intermediate variable. For every intermediate variable you get a path, for every path you get a term. It's just a point of view, right? You don't really have to use that point of view. I think it's very efficient, very convenient. Oh, one thing to keep in mind. It is tempting to say, you know what, I'm just going to memorize the formula. Here's the problem. The variables aren't always called what they're called in this picture. Sometimes they're not called x's, y's, and z's. Sometimes they're called p's, q's, and r's. Sometimes in one space, the variables are k, l, and q, and in the intermediate space, they're p and r and z, and then in the other space, they're aleph, and zeta and x, right? You can't memorize all possible forms, right? And again, you don't want to have to write down the great big bulky matrix form first and then think about matrix multiplication and then infer your corresponding chain rule. That's super inconvenient and super inefficient. Much better, I think, to understand this point of view of paths and intermediate variables contributing to terms. Glass smooth, easy to do. Okay. All right, so let's see an example. Here's the question. Got a couple of functions given. We want to compute one of the partial derivatives. Now you'll notice, in order to be able to take this point of view, I need to be able to look at my diagram, because the diagram is where I see the paths, and it's where I distinguish, as I think as clearly as possible, which variables are, in fact, the intermediate variables. Right? So I am a huge proponent. I strongly encourage, I stop short of saying require, but I am a huge proponent of draw yourself a diagram, right? Connect the dots of the variables like I've got there, tailored to your scenario, so you'll have a cheat sheet, right? That will always guide you toward the right answer. And why not give yourself that cheat sheet? By the way, side note, it also, if you draw a diagram that actually makes sense, you are demonstrating understanding a little bit, right? And that's where points come from. So you might even get a little partial credit just from writing down the diagram. Right? So strongly encourage that. So let's do so here. Notice F takes X's as the inputs and gives Y's as the outputs on my diagram. Notice G takes Y's as the inputs and gives Z's as the output. There you go, on my diagram. Now that I've got my diagram drawn, I can see which variables are where. Oh, let's see, by the way, I'm interested in the partial of Z2. There it is. With respect to X2, there it is. What are all the possible paths? Where do my terms come from? Well, I have, it would seem, a Y1 path. I get a Y1 term. And then I also, it would appear, have a Y2 path for the Y2 intermediate variable, and I have a Y2 term. Notice that in each of these terms, the terms always fit the same form. Let's see here. The Y1 term has partial Y1s there and there. And again, they don't cancel, but they are there and there. Notice that that is still that, and that is still that. And that pattern continues. If you look at the Y2 term, that intermediate variable Y2 is in the analogous spots, and the partial Z2 and the partial X2 are in the analogous spots. So that pattern holds. Very nice, very convenient. Make sure you're clear on how that pattern works. Again, it streamlines the process. Yeah?
Why are those arrows pointing like X2? Like, where are those arrows from?
The arrows in the diagram? Yeah, it's just sort of reproducing sort of the argument that we made here, which is that, look, when you make changes in xj, there are consequences to that, right? One of the consequences, when you change the input to the function, you're going to change the outputs as well. So I draw the arrows as a way of representing a causality. So changes in xj cause changes to y1. And so that arrow is an indication of this change is causing that change. Does that make sense?
Wouldn't changing x1 also change y1?
Yeah, and if I were interested in a partial with respect to x1, then I'd be worried about that. Yeah, absolutely. But very importantly, here the question is about a partial with respect to xj. And when you're taking a partial with respect to xj, all the other x variables you hold constant. Is that satisfying?
Yeah.
Yeah, okay, yeah. Cool. Okay. All right. So now notice I've now written down my chain rule appropriately. appropriate to this circumstance, appropriate to how the functions are described, appropriate to the roles that the names that I've given to the variables in this story, and I didn't have to memorize it, and I didn't have to write down the whole derivative matrix and think about matrix multiplication and a bunch of much more bulky and inconvenient and slow stuff. I just look at the intermediate variables, boom, write down the formula. And then the rest of this is you compute some partial derivatives and etc. Okay. All right. All righty. So, a couple of heads ups. We're good on time. Okay, that's super. Confusion of variables. It's a really easy mistake to make. Again, I've been teaching multivariable calculus for a long time now, and I've seen this kind of mistake tons. And the more I dwell in class on certain categories of mistakes that I see over and over again, the less I see those mistakes. So I think that's a good thing. That's why I'm going to dwell on this, and this is going to seem silly, right? But nevertheless, it is easy to mess that up by not being aware of the threat. Okay, so here it is. We're going to start with a single variable example. Here's a couple of single variable functions. No problem. F, perfectly reasonable single variable. G, perfectly reasonable single variable function. The question here asks, I would like to take a derivative of the composition. And in some sense, we already have a problem. I'm not going to reveal exactly what that problem is just this moment. Okay, but that said, let's derivative of the composition. Now I'm going to play fast and loose with the notation here to be more dramatic about my point, right? And so I'm going to just write down the derivative of the composition, the product of the derivatives, right? And look, it's really easy to write down, for example, what is g prime? Well, the derivative of x cubed is 3x squared, isn't it? And let's see here, the derivative of f, well, the derivative of x squared is 2x, right? So it would seem, right? And then you multiply and you get this answer, which of course is obviously wrong. Of course, the mistake that we made is I was sloppy with the notation, and then I paid a corresponding price. And of course, the second derivative, the derivative of the second function, has to be evaluated not at x, but at f of x. And y'all probably remember that from, I hope you remember that from Calc 1, chain rule. By the way, reminder, opportune moment, reminder, if you are in fact maybe a little not clear about some of the Calc 1 assumptions that I make, that I assume that you know, come talk to me, right? I'm happy to help. If you're not clear about why that's the case, why do we have to put the f of x in there? We just need to get that straightened out. Come to office hours. It's right after class. I'll show you. No problem. Don't carry around a misunderstanding, right, for the rest of your life. Just come ask me. Okay, so we're supposed to plug in to the derivative, g prime, the derivative of a cube being 3 times the square. What we have to plug into that is, in fact, f of x, not x. And so when you do that, yes, okay, yada, 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 it does get you to the right answer. But can we agree this is awkward and confusing? You have to remember what to plug in. You have to remember as you're writing down the derivative that the thing you plug in for x isn't actually x, it's actually f of x, and oh my gosh, super confusing. All right, so let me just show you how to avoid all of this. And again, we made a mistake from the very beginning. As soon as this question got asked, as soon as that happened, it was implicit that we were composing functions. Look at that. It says so right there, g compose f. Well, wait a minute. If you're composing g and f, and if f takes x as its input, what am I going to call the output from f? Can I call the output also x? Nonsense. The input is x. The output I have to call something else. And if the output from, when you're composing, if the output from f needs to be the input to g, that means that you need to reconceive of g not as a function of x anymore. You need to reconceive of g as a function of y. Now, it's the same function. G is still the cubing function. It's the function that says, hey, whatever you give me, I'm going to cube it. Same function. I'm just writing it in terms of a different dummy variable. Everybody see that? Okay. And, all right, now again, this is just right and proper. I mean, not doing this is just allowing a confusion of variables to stand, and that, why would you, we don't want confusion of that's, why would we do such a thing? You should always do this, right? And then having done that, hey, notice the problem just goes away, and check it out. I'm going to write down the same fast and loose, careless, one might say, formula for the single variable chain rule here, the derivative of compositions, product of derivatives. I'm not making any note about what is evaluated where. Notice the derivative of whoops, wrong color. The derivative of f, I write down. The derivative of g, I write down. And oh, cool, I now have a visual reminder that this thing called y, being as it is the input to the g function, must also be the output from the f function. Plug in x squared where y is. I mean, I didn't have to remember it. I'm just following the instructions of how I've agreed that this problem naturally should be set up anyway. Right? I didn't have to remember anything. The notation did it for me, and we get the right answer. Right? So, I think this is how they ought to do single variable chain rule. Don't confuse the variables, for crying out loud. It's just, it creates potential to step on a landmine. And you avoid the confusion of variables, the problem disappears. Okay. All right. So now, again, why do I talk about single variable? I know y'all know single variable. Well, it's because the same problem happens in a multivariable context, right? And so here's a couple of multivariable functions, and we could reasonably be asked what's the derivative of the composition, and we've already got a problem. There's nothing wrong with f, there's nothing wrong with g, but as soon as I say I want to compose them, I've got a confusion of variables problem, and you've got to fix that before you do anything else. So, all right, now again, f seems to be written in terms of x's and y's, so I guess I'm going to do that. The outputs from f, I can't call x and y, obviously. That'd be confusion of variables. And that means that the inputs to g cannot be called x and y. So I've got to take that formula for g, I've got to rewrite it in terms of different dummy variables. Now again, I'm not changing g. It's the same g, same function. I'm still doing the same process to whatever inputs you give me, I'm going to go through the exact same process. It's the same function. I just write it in terms of different dummy variables. Landmine avoided, right? And now, again, I can just write down the chain rule. Derivative of the compositions, product of the derivatives, handy. Take the appropriate derivatives. Don't forget the one that's on the left in the algebra is the one that's on the right in the diagram, right? So what you get by taking that derivative has to go on the left. And the function that in the diagram is on the right, its derivative, the function that in the diagram is on the left, its derivative matrix is on the right. So when you go through this process, it's going to go to the right. Super easy to mess that up, right? Heads up. There's no workaround I'm aware of that's, reasonably consistent with conventions that won't create more problems than it solves. So make sure to think carefully about the order that you write down those derivative matrices. Okay. All right. Okay, and then multiply. And don't forget to plug in at the end. Let's see here. Having set things up as we did, what do I do with this u right there? Well, u, being the first input to G, is also the first output from F. And so plug in accordingly. Likewise, what do I do with this V here? Well, that V is the second input to G. That means it's the second output from F. And we plug in. Oh, you know, I kind of missed there. Let me, here. Do it like this. There we go. Again, plug in accordingly. Okay. So, all right. Here's another problem. Another big problem. Don't play too fast and loose with these diagrams. Now, a diagram like this, yeah, sure, fine, this is good. Why is this diagram fine? Well, because this literally comes out of a composition of functions. I've literally got a function here. x1 and x2 are the inputs, y1 and y2 are the outputs, and I am straight up, no asterisk, composing that with this function here, where y1 and y2 are the inputs, right? The outputs from F are the inputs to G. And then Z1 and Z2 are the outputs. And everything's fine. I'm literally composing functions here. By the way, that's where our that's where our chain rule came from, right? Everything that we have concluded about the chain rule way back, oh my gosh, way back, it all comes from this matrix take on what is in fact an actual composition of actual multivariable functions. Right? Okay. All right, so now that noted, yeah, we can rewrite that with diagrams, but that doesn't mean that any diagram that you write down necessarily comes from an actual composition of functions, right? And the only chain rule we have in this, so far anyway, at a minimum, the only chain rule that we know is what happens when you're composing actual multivariable functions. And this diagram isn't that. Right? What are the two functions that I'm composing here? Look at this weirdness. This variable appears to be functions of, well, I mean, y1 and y2, right? But also x1. One of the inputs to the second function, it would seem, is also an input to the first function, it would seem. That's not how composition works. So we don't know squat about any sort of a chain rule that relates the variables per that diagram right there. Not a thing. All right, so be real careful about that. You can get into big trouble messing this up. So for example, just as a for example, not only do we not have a chain rule, I claim it's not even clear what this even means. Partial of z1 with respect to x1. I know what it means on the left. On the left, it means, well, there's z1, there's x1. We're looking at the composition. The composition starts from this domain. I keep all the other variables constant, so I'm going to hold x2 constant, and boom, take a derivative. That's not confusing. That's not a problem. That's all fine. What does it mean over here? So I'm going to think of that as being a function of that, and then wait a minute, am I supposed to hold y1 and y2 constant? I can't. I can't hold y1 constant. It's a function of x1. How do I hold it constant and change x1 at the same time? That doesn't make any sense. Right? Everybody see the problem? It's a nasty little problem. And here's where it gets even worse. This kind of stuff comes up right? So let's look at this down here. Let's look at this question. Now here's several equations, and if you note, these equations, if you were to kind of connect the variables one at a time, in fact, you would produce that diagram. So in a situation like this, if the question says, hey, what's the partial of z1 with respect to x1, what does that even mean? This is a nasty little problem, right? So, by the way, it could mean, and I should also note that this is in the established notations for this kind of a situation, and the convention seems to be that the reader who's reading work that uses the chain rule here has to interpret from context, right? And again, it's not satisfying. Wouldn't it be nice if notation always unambiguously meant something clear? It doesn't. I'm sorry. It's, again, not my fault. Right? I'm just the bearer of the bad news here. But it could mean, and we will be making use of the idea of pretending that these other variables don't exist, looking at how this is a function of those, ignoring that y1 has any sort of dependence on x1, holding these variables constant, right? And then looking at that one partial derivative. That's one thing that we're going to have to do something with in some cases, but then it could also mean, hey, altogether then, look, there's a direct contribution to x1 changing z1, then there's the by way of y1 contribution, and then there's the by way of y2 contribution, and I want to know altogether what's the total rate of change of z1 with respect to x1. That's going to matter too, right? So we have a real notational confusion problem here, and here's how you fix it. All you got to do is introduce a new variable right there. In this case, anyway, we just introduce a new variable right there. I'm going to call it x1 star. It is just literally x1. It has the exact same value as x1. I rewrite this accordingly as x1 star. And now, with that established, notice that this collection of equations gives me that diagram. Oh, and don't forget this one as well. And this diagram has no confusion of variables problem. You apply the chain rule. It works. Unambiguous. No problem. That's how you do that. Okay, I guess we're out of time. See y'all later. I'm sorry I went over. See y'all later. Have a good one.